Alright, thanks for watching, and today I'll give you a taste of topology because I'll define what it means for a set to be open. And for this, we first need to define the notion of an open ball. So let SD be a metric space. And what does it mean to have an open ball? Well, think about this in terms of, let's say, RK. What is the ball center of X and radius R? Well, it's really just a set of points that are at most R away from X. And in fact, it's the same definition here. So the ball, open ball centered of X and radius R, is just a set of points Y, such that the distance between X and Y is less than R. And in fact, let me give you a couple of examples of balls. So, for instance, in R2, you can consider the ball centered at 1, 2 and radius 3. Well, it's just a set of points that are at most 3 away from 1, 2. So, in other words, this is the ball centered at 1, 2 and radius 3. More interestingly, let's see what it means to be a ball in R. So again in R. And it turns out balls are very easy in R. And let's think about this. So what does it mean for a point to be at most R away from X? Well, the open ball here, it turns out it's nothing other than the interval X minus R and X plus R. Because those are the points that are at most R away from X. So BXR in this case is X minus R and X plus R. Okay, now that we know what an open ball is, we can finally define what an open set is. And it's kind of neat. So, what does it mean for a set E to be open? Well, it just means that no matter which point in E you pick, there's always a small ball that's included in E. In other words, for any point in E, there's always a small enough radius such that the ball centered at X and radius R is included in E. So, definition. If E is a subset of S, then E is open, technically open in S, if for all X in E, we can fit some small ball inside E. So there is a small enough radius such that the ball centered at X and radius R is included in E. In other words, what does that mean? It means no matter which point you pick in E, you can always move around a little bit and still stay inside E. And in fact, we'll see this is not true for not open sets. So we always have a little wiggle room, which is actually very nice to have. So sometimes you say, well, if X is in it, then the family around X is also in it. So now, let me give you a couple of examples. For instance, in R, the interval a comma b is open. And why is that true? Well, if I give you any point x, you can always fit a very small interval inside a comma b. In other words, there is always r small enough such that the interval x minus r comma x plus r is in that interval a comma b. So, because if x is in a comma b, then there is r positive such that bxr, which remember is just the interval x minus r and x plus r, is actually included in a comma b. So no matter which point you pick in the interval, you can always fit a small ball inside it. And if you're curious what is r, well, the smaller one of those two distances, so x minus a and b minus x, namely let r be less than x minus a and less than b minus x, right? You can show that this does the trick. Another example of open balls, another example of open sets is just what you think it is. The open ball itself is an open set. So bxr is always open. Why? Because consider again this huge ball, bxr, that is x and that is r. Well, look. No matter which point you pick in that ball, let's say y, you can always fit a very small ball inside of it. In other words, no matter which y you pick, you can still move around a little bit and still be in that ball. All right, now let me give you an example of a set that's not open so you can really understand what open means. So non-example 3. So consider the closed interval a comma b. And I'm claiming this is not open. What does it mean for this to be not open? It means there's some culprit, which here it's a, such that no matter how small r is, the ball centered at a and radius r isn't included in your interval. In other words, what this means is, no matter how small you move away from A, you could get outside of the interval. So there's not always a ball that's included in your interval. So not open, because no matter how small r is, no matter how small r is, the ball centered at a and radius r, which is a minus r comma a plus r, is not included in your interval. And that's very different from the open interval, a comma b, because open here means no matter where you are in that interval, you can always fit a very small ball inside your interval. But here it's not true. Here at A, there's no way of fitting a ball, even if the radius is absolutely tiny. And some say A is an edge or a cliff, right? So if you just go just a little bit less than A, then you're not in it anymore, okay? All right, and again, that's why we like open sets, because we have some wiggle room. Here you don't have any wiggle room at A. And in fact, in a similar way, A comma B, so closed A, open B, and open A, closed B are not open. All right. So now that we've seen examples of open sets, let's prove a couple nice properties about open sets. And you'll see this is very exciting. It leads me to an exciting subject in some sense. So facts. Well, first of all, the empty set is always open and S is open. This I won't prove, you can just do it, using the definition. Moreover, here's the interesting thing. Suppose you have any collection of open sets, and you take the union, meaning sort of everything, then it turns out that union is also open. So the union of any number open sets is open. And you might ask, is the same true for the intersection? Not quite, so almost, but provided we just take finite number of intersections. And I'll give a counterexample in a second. So the intersection of finitely many open sets is open. In other words, let's say if you take the intersection of 3 open sets, that's open. But careful, this is not true for infinite intersections. So let me give you a non-example. Take UN to be the open set, let's see, -1 over n and 1 over n. So you see U1, that's just the open interval -1 and 1. U2, it's the open interval -1/2 and 1/2. U3 is the open interval -1/3 and 1/3. And the question is, what is the intersection? Well, kinda, those sets converge to 0 in some sense. So in fact, the intersection is just 0. In fact, it is 0 because 0 is included in all of those sets. Then, the intersection of the UN is just the 0 set, but the 0 set is not open. There's no way to fit a ball in the 0 set. So that's why it's very important to take finite many intersections. All right, now why do I find that so exciting? Because it turns out any set, okay, that satisfies those 3 properties, it's what's called a topological space. So after this fact, we know that any metric space is a topological space, but not every topological space is a metric space. And the study of such kind of topological spaces, it's what's called topology. So topos logos, the study of places. And topology, it's a very nice ally of math. That's why I respect it, because I guess an ally of analysis, because a lot of analysis facts can be proven using topology, like the Baire category theorem, or Tikhonov's theorem, or the Tietze extension theorem, etc., etc. All fancy words, so that's why it's very useful in analysis, but it's also a field of its own. So topology, you just study objects where you don't really care about distances, but more about open sets. All right, now let's just continue with a very small topic related to open sets, because, well, unfortunately not all sets are open, but you could still have that for some of the points, there is an open ball that's included in that set. And those points, we call them interior points. So definition, so if E is any subset of S, then X is called an interior point. If there's some small ball around X that's in that set. So if there is R positive with BXR is included in your set. So it's like openness, except it's specific to this point. So we're fixing X and we're asking, is there a ball around X that's in your set? Okay? And in fact, those points are so important, we'll put them usually in a collection. So definition, if I write E circle, kind of circle like a ball, it's just the set of all interior points. Of E. It's like interior design, but for topology. So for instance, okay, let me just show you a couple of examples. For instance, if you take the closed interval 0, 1, well, let's ask what the interior points are. Well, look, anything strictly inside 0, 1, you can fit a little ball. So anything inside 0, 1, it's an interior point. There's always a wiggle room, but 0 is not an interior point because there's no wiggle room around 0. You cannot fit any ball here, and you cannot fit any ball around 1. So in fact, the set of all interior points is just this open interval 0, 1. So it is always true that the interior points are less than your set, but you could also have something crazy. For instance, what are the interior points of the rational numbers? Well, notice, for the rational numbers, you can never fit a ball around x that is in Q, because there are a lot of irrational numbers in any neighborhood of x. So the question is, what are the interior points of the rational numbers? There are none. For no point can you fit a ball inside your set. So in fact here, the the interior point is the empty set. And last but not least, what about the interior point of 0, 1? Well, any point here is an interior point. For any point, you can fit a little ball. So the interior of 0, 1 is just 0, 1. And in fact, you may notice this is the same. This is true for any open set. So in fact, E is open if and only if the interior of E is equal to the set. Because again, what does it mean for a set to be open? It means no matter which point you pick, you can fit a ball. So the interior in this case has to be the whole set. All right, thank you so much. And next time we'll do closed sets.